start the recording. Thank you. Yeah, this webcast is being recorded and it will be made available to the public. So in case if anyone has missed some of this content, you can always view the recording later. Okay, and it will be available at EPRI website and also DTU website. Yeah, good morning and good afternoon, and thanks for joining today's webcast on holistic approach to reduce offshore wind turbine costs. So the content that we are going to present today is funded by European Funding Commission. We started this work back in 2020, and we are nearing completion on this project by this June. So coming to today's agenda, we'll just quickly go through DTU, Denmark Technical University, and EPRI introductions. And then we'll give a high-level overview of Hiperwind project. What are the overall goals and where we are as of today. Asger from DTU, he's going to present on the model that he has built, the physics-based model that he has built to predict the life of a main bearing on Siemens 2.3 megawatt offshore wind turbine. Later, Clement is going to talk about the LCOE model and what are the inputs considered for this LCOE model for offshore applications, and also a quick demonstration of this model, followed by a quick summary and next steps. Just a quick intro about EPRI, in case this is the first time if you are hearing about EPRI. EPRI is a non-profit organization founded back in 1972. We recently celebrated our 50th anniversary. We have worldwide presence with overall employees about close to 1,500 and revenue about $420 million. Our main customers are owners, utilities, operators. We work with more than 400 entities worldwide, and our headquarters in Europe is in Dublin, and that's where the Wind Europe technical workshop is going to be there, and also dissemination of this Hyperwind project is also scheduled during that event. So we will cover that at the end of the webcast. And I'm going to hand over the discussion to Asger. Asger, please take over. Thank you.
Yeah, thank you, Roger. So this is kind of a short presentation to the DTU Wind and Energy Systems Department, which is part of the Technical University of Denmark. And what I've just shown you is sort of a fast overview that we are about 400 people in the department, about 15 professors. We are sort of 190 researchers, and we have about 100 PhD students working all on the mission on, let's say, getting wind to work in different energy systems. Our revenue is like 32 million, and you can kind of see that we're heavily research oriented and funded by a lot of research funding organizations and bodies. And the example you see today is Horizon Europe. Just a fast overview of our department. We have 4 major divisions, which are the first 4 blocks there. So we have wind energy materials is one division. How to build wind turbines is another one, how to design them. Then we have a division on wind energy systems. And finally, we have a more larger view on that, which is the entire power and energy system division. And with that, I think I will give it back to Roger. I'll give it to Clemens, right?
Thank you, Asger. No, and I will take the next slide. Thanks, Asger. All right, thanks for the introduction. So I think we've already said 5 times the word Hyperwind. So maybe just allow me to give you a short introduction of what this project is. So it's under the 2020 Horizon Research Innovation Program. So the project started It's actually close to the end. Hyperwind stands for highly advanced probabilistic and enhanced reliability methods for high value cost efficient offshore wind. Quite a mouthful. So yeah, just stick with Hyperwind. You have the link here if you want to see what the program is doing, but basically it's aiming at improving the competitivity of offshore wind in the context of the European Commission target to install 450 gigawatts of offshore wind by 2050. So there is a real need to increase the competitiveness of that technology and make it a more industrialized technology. Let's put it that way. And so Hyperwind aims at reducing the uncertainty throughout the entire design process. So really starting from where you start looking at what is the wind at a given location, to how do you assess the wind condition of the turbine, how do you assess the loads, and also how do you model the lifetime of your turbines, how do you accurately anticipate your O&M. So it's really looking at the entire spectrum. Today we're going to focus on the reliability part and operation side of things, but just to give you a heads up that the Hyperwind goes a bit beyond that. And the target is to deliver a reduction of the LCOE by approximately 9%. So throughout the entire process, it's not just what we're going to present today. So we can, but it's quite an ambitious target of reducing the LCOE by 9%. So the project overall will last for 45 months. It started in December 2020 and will end in September this year. We recently got a slight extension of the project, but we are currently wrapping up and packaging everything. And it's kind of a wide and diverse participants. So DTU is the lead of the project. EPRI is involved. There is also people from ETH Zurich, University of Bergen, EFPEN in France, DNVGL, EDF UK, EDF France. So industrial and academia all working together for improving the technology. So how do we measure the success in Hyperwind? I mentioned it's about reducing the cost for the turbine. So the metric that comes most often when we discuss about the cost of an energy production is the LCOE. It's basically don't worry about the ugly equation here. It just means it quantifies the cost, so how much dollar or euro you need to produce 1 unit of energy. So it has the benefit of encapsulating all the expenses on the numerator and what is produced on the denominator. So it's a relatively simple metric, especially if you want to compare across different sources of energy where you need to consider different things if you're talking about gas or nuclear or coal against offshore wind. So it's a convenient metric. And yeah, for Hyperwind, we really ambition to reduce the cost. So from on all aspects of the capex, reducing the capital you need, it's mostly because if you get smarter at designing your turbine, you can remove some conservatism, and ultimately it leads into lighter components. So you need to pay less material and your turbines get cheaper. On the operational side of things, by improving the maintenance schedule and also anticipating when your components are failing, you can replace them more efficiently. You reduce the expenses because you can book the boats in anticipation. When you're talking about changing component offshore, there is a strong aspect, which is the vessel availability. So by getting improved techniques there, we can also reduce the LCOE. And then there are some more marginal benefits, I would say. If the technology gets more mature, the banks will tend to trust you more, and you can reduce the interest rate, which in the end will have a beneficial impact on your project cost. Similar, if the design process becomes a bit more streamlined, you reduce the development cost. And as a side benefit as well, if you're better for preventive maintenance, you also improve your wind farm availability, so you produce more. So all that I've mentioned before was trying to reduce the denominator, but we're also working into increasing the denominator to reduce the LCOE. So all that, when you add it together, gives that target of 9%. Just a quick overview on how the project is organized. I mentioned that it's really looking into predicting the wind conditions to anticipating the maintenance. So, and this is kind of reflected in the work package. So there was an effort at the beginning where we collected the data, then people focused into accurately modeling the ambient conditions for that wind farm. That was work package 2, that delivered for work package 3, which was really trying to model the flow in the wind farm, understand the wind condition of each of the turbines to identify the turbines that were the most problematic from the design point of view. Then work package 4, a big chunk was into assessing the structural components, so really designing the foundation and the tower of the turbine such that they can resist for the entire project lifetime, but at the same time removing the conservatism. And today we're going to discuss about work package 5, or Asger is going to present his finding on work package 5, which is a life assessment of the main turbine components. And after that, I will present on work package 6, which is basically gathering the inputs from all the other work package and trying to convert that into an LCOE calculation and come back to this 9% and see if we meet that target or not. So for today's agenda, we will have essentially 2 big chunks. First, Asger is going to present on this advanced reliability model for turbine components. It's really like demonstrating about how physics-based model coupled with site-specific information can be used to accurately assess the remaining useful life of the components. And those information those are inputs, then you can inform your OEM planning if you're better at predicting when your components are going to fail. And it's mostly going to be a proof of concept on the main bearing, but the methodology can be applied to different components or other critical components. And then I will present a more holistic approach where I will discuss how we can take those inputs and generalize basically the concept and how can we use that to being better at predicting O&M budget and what is the impacts that it has on LCOE. So we're going to present that on one case study, which is the Teesside wind farm operated by EDF in the UK. But I want you to take more that as a showcase, like a proof of concept of what we are doing, and keep in mind that everything we develop in Hiperwind should be applicable to any wind farm. And should you have any interest in seeing those methods applicable, you can always contact us. Okay, so I'm going to stop talking and hand it over to you, Asger, for your presentation.
Yeah, thank you, Clemens. So let me just switch to the next. Oops, that was not what I wanted. Sorry, wrong button. Okay, so this is the outline of my presentation. So I'll dive into a little bit on the drivetrain of the turbine sitting at the Teesside wind farm, because this is the input we have used for asking the question, can we now predict the lifetime of these components? So the Teesside wind farm kind of looks like here. It's sort of very close to the coast of the UK, operated by EDF, 27 turbines in 3 rows. And the turbine which are sitting on these rows is the Siemens wind turbine 2.3 megawatt with a 93-meter rotor. Here is sort of an illustration of this drivetrain. And what you see is we have basically a main bearing sitting here, a gearbox sitting here, and then we have the generator at the back. And what I will delve into is how to get information about these components in order to assess the lifetime. So we will look into the main bearing life model proposal. We will look into how did we take the environmental and operational conditions of the wind farm, pass that on to the turbine, and then mitigated that into the main bearing. For this, we need to talk about some air elastic load estimations, and then we will delve into what life predictions are telling us in terms of the environmental conditions and in terms of the operational conditions. And finally, this is giving some inputs or some, let's say, inspiration to what is the expected operation and maintenance schedule of the farm in terms of the main bearing of these turbines. Okay, so the first challenge we were facing is, of course, how do you get information about the components sitting in the drivetrain? And this is, of course, not that easy because it is often not something the OEMs are sharing very easily. But when you're looking into old machines, and the Siemens wind turbine 2.3 megawatt 93 meter machine is to be considered a pretty old machine, because the Teesside wind farm was installed in like 2011 and operated a few years later. In order to identify the components, we were looking into spares in motion and looked for spare parts for this turbine. And that actually turned out to be a way of finding a representation of what we believe are the main components. And here is just shown sort of some of the components that we managed to identify. And originally we were thinking if we could investigate the lifetime of the gearbox, but that turned out to be not possible to get the information about, let's say, the layout and the bearings inside the gearbox. So we have sort of focused on the identification of the main bearing for the turbine, which is known as a FHE 230/800 main bearing. This is just an illustration of how such a main bearing looks like. So it has an inner diameter of about 0.8 meter. It has an outer diameter of 0.2 meters, and the width of this bearing is about 0.3 meters. And the weight is about 900 kilograms. So this is just for you to get a feeling of how big is this object, which is now sitting here supporting the main bearing of the turbine. Another thing that is kind of crucial is to figure out what is the grease that is used to lubricate this bearing. And again, we were looking for a representative. We're not saying this is the entire truth, but a representative grease could be the Kluberplex BEM 41-301. And having this information, we were actually then able to ask the question, can we now simulate the turbine and mitigate the loads into this main bearing? In order to do so, we needed to formulate an aeroelastic model of the Siemens wind turbine 2.3 megawatt 93 meter rotor turbine, and the tool that was used for that, for the DTO part of the work, was the HAUK2 aeroelastic code, where a model representation of the drivetrain or the nacelle was created. Several other aeroelastic tools are being used in the project by other partners, but the HAUK2 code is what we do from a DTU point of view. So in this kind of aeroelastic model, you represent the main components of the drivetrain by beams. So the rotor is attached here to the hub flange. We have one beam, and then this is where the main bearing is sitting. The main bearing is then connected to the gearbox, and we have an output beam of the gearbox, which is the high-speed shaft, which then enters the generator. And you can kind of say these beams sitting here is the support of the main shaft and the generator, or the drivetrain, or the gearbox, you might say. And then basically this is all attached to the tower. So having the aeroelastic code, we are able to sort of mimic what are the wind conditions hitting the rotor going to do in terms of the forces that will hit the main bearing. So with this tool, we will be able to simulate what is the axial load and what is the radial load on the main bearing as function of time whenever we expose the turbine to a turbulent wind field. So over here, the radial, the axial load is going to push the rollers backwards, you might say, whereas the radial load is going to push the rollers sideways. So in this way, you can kind of say that the radial load will be basically the gravity of the rotor resting on the bearing, and the axial load here will be the thrust, or the push that will come on the rotor plane into the bearing. So once we know what the bearing is, we can also look up sort of the specification of this bearing from the bearing manufacturer. And what you learn is basically how to get the load on the rollers, you might say, or the load of the bearing by combining the radial and the axial loads, and you get these geometrical factors here. What the bearing manufacturer will also tell you is, if you now want to calculate the lifetime of the bearing, you can use, let's say, a very simple version of how to evaluate the life of such a bearing called the ISO 281. The lifetime of the bearing kind of comes out in an equation that looks like this, saying you need to know the capacity of the bearing. This is what you get from the catalog. And then you need to evaluate what are the bearing loads hitting the bearing. And then in principle, you need this exponent, which from the standard is about 10 raised or 10 divided by 3. So that is the exponent here. Now, in order to calculate the loads here, you will have to do sort of an averaging over all the time series. And the way you do that for bearings is to evaluate for how many revolutions, those are the kind of the L's going into the equation, is the load at a certain level. And then you will have to feed to calculate the PD. By averaging over all the time series and then feed it into the L10H equation here at the bottom. So once you are doing this, you would also have to specify what are the environmental conditions of the turbine. And here are the usual wind speed distributions you would get from what is known as the IC standard. So you can kind of see that there's something called the IC class 1, 2, and 3, where the average wind speed of the distribution is kind of given by where do we find this peak here. So you can kind of see that the yellow is the low wind speed and the blue is high wind speed distributions. Besides just what is the wind speed in terms of how many hours per year do we have a certain wind speed, we also need to specify the turbulence intensity, which you can see on the right-hand side. And again, the IC standard is usually specifying it with the equation you see below the graph, where you will have to sort of specify the reference intensity, this IREF, which you can see as the label in the top of the graph. So basically what we can do with this now, we can specify what is the wind in terms of wind speed and also turbulence intensity is hitting the turbine, and then we can start simulating what would the load time series be on the main bearing. So the graph here are showing the radial load, the axial load, and then we need to combine these two into the bearing load, which you see on the right-hand side at the end. And basically, this is the main load going into the bearing. And what you kind of recognize from this graph is that it peaks up at 10 meters per second, which is basically the rated wind speed of the turbine. And then it falls off when we get to higher wind speeds. And this is basically a replicate of what is known as the thrust load of the turbine. Which is also the same as you can kind of see the shape of the FA curve in the middle. So now we are actually ready to say, now we know the loads hitting the bearing, and we are ready to feed that into the life equation. And once we do that, we will get a basic life at the left here, where you can kind of see that if the turbine was operating at 5 meters per second constantly for its lifetime, or just constantly, the main bearing would last for 600 years, or between 400 and 600 years. But that's also a point where the load is small. So we would then now try to look at, if we get to 10 meters per second, you can kind of see that the life is actually getting lower. And then if we increase the wind speed, then the life of the main bearing is increasing again. But the wind turbine is operating at different wind speeds, doing its, let's say, 1 year of operation. And now if we do the averaging over the different hours of operating at different wind speed, we get the right-hand curve, where you can see that the expected life of the main bearing is coming out about 40 years at a turbulence intensity of 10. And then if we increase the turbulence intensity to 18, the life is actually increasing up to like 42 years. However, this is only evaluating if we put in the loads. But the ISO 281 standard is also trying to say something about what if the grease of the bearing is getting dirty or is very clean. So there's a cleanliness to the grease that you can also include. And this is basically feeding into what is the viscosity of the grease in the bearing. But the viscosity of the grease is heavily depending on temperature. So in principle, what we tried to do now was to include a temperature model saying, if we take the frictional forces inside the bearing and try to solve for what do we think the temperature should be, you can kind of see the top graph is our first attempt to do this, where we would get a relatively low temperature at low wind speeds, but when we get to rated wind speed, we will get a high temperature, and getting to even higher wind speeds around 20 meters per second or 25, the temperature should come down again. Below, you can kind of see that would be the graph below shows how the viscosity would change with these different temperatures. Below, you can see the equation saying this: the modified life is then the original L10 life, but now we need to multiply it by this ISO factor, taking into account the viscosity, the temperature, and so forth. And we can also multiply it by this A1 factor, which is saying we would be able to change the reliability level of the L10, because the meaning of L10 is that 10% of a fleet of bearings or an ensemble of bearings is expected to fail when you reach this lifetime. So if we want to calculate the lifetime not to be 10% of the, let's say, a population of bearings failing, we can change that to 1% or to 50% by changing the A1 factor. But we will come back to that. So what we tried now was to look for this ISO factor. And if this is showing signs of getting below 1, then the life is actually reduced below the original determined life. And with the current setup of the equations, we now see that there is a possibility to get a change of the life from, let's say, 22 to 50 years by changing the turbulence intensity of the wind. If we're changing the mean wind speed of the wind, we don't see that much of a change in terms of the life. And our hand-waving attempt to try to explain what is going on is basically that the very painful peak at the top of the thrust curve is what will bring the life down of the main bearing. And as we increase the turbulence, we're kind of moving away from that peak. And that is the argument why that if you increase the turbulence, you actually get a longer life, which is kind of intuitive compared to what you might think. Okay, so now if we want to try to interpret the reliability level, what we could do is to say, if we look at the T-farm wind side, or the T-side wind farm, we could ask the question, if one bearing out of 27 should fail, that would be a failure rate of 4%, which would be equivalent to a reliability of 96%. So what has been shown here is when the reliability crosses this line, we expect 1 out of the 27 bearings to fail. When it crosses this level, it should be 2 out of 27. This level is 3 out of 27 bearings, and this is 4 out of 27 bearings failing. So basically what the ISO 281 standard is trying to tell us is we should expect between 1 to 4 of the main bearings to fail in the 25-year lifetime of the wind farm. And now I'm including, let's say, plus 10 years of life extension, then we might get to 4 bearings. What the standard will not be able to say is which of the turbines that will fail. So the statistical reading of this is 1 out of the 27 or 4 out of the 27 turbines will have a main bearing failing. But we will not be able to tell which of them. And this is, of course, with the assumption that all the 27 turbines run under the same conditions. You might pose the question that our previous temperature model showing we should have 70 degrees on the main bearing is a bit high. And of course, we have worked on refining this temperature model quite a bit. And you can kind of see that our current simulations are showing that we should probably get 40 to 50 degrees. And of course, the temperature of the main bearing will now also depend heavily on what is the ambient temperature outside the turbine. So for the T-side wind farm, we will be having an outside temperature between 5 and 20 degrees. So you can kind of see that we now also will have different temperatures around the year, and this is hinting at that our analysis should in principle be expanded to have a monthly variation instead of a yearly evaluation. Okay. Finally, we have also dived into this effect that if we increase the turbulence intensity, life goes up, has been investigated by adding many more points to the air elastic simulations by, let's say, probing the peak of the thrust curve a bit more in details. And this is showing that it's not just an artifact of not sampling the properties of the thrust curve correctly. With the new temperature model, we might, however, see that the life is probably coming up, or it could come up quite a bit if we're running with very clean grease. But we also need to sort of look into what if the grease is not super clean. What would the consequence for the main bearing lives then be? And this will bring me to the conclusion that well, we have demonstrated that we could describe the main bearing of the Siemens 2.3 megawatt 93 meter turbine, identified the main bearing type, the grease of it, and using the air elastic method here, we have sort of indicated that the life of the main bearing is somewhere in between 22 to 40 years, which we have translated into about 1 to 3 or 4 of the main bearings of the T-side, of the 27 T-side machines, is expected to fail during the 20 to 35 years of operation. What we are working on is a map which is trying to take into account what if we are describing the local wind conditions of each turbine. Then we might be able to say something about some of the turbines might be more heavily loaded and could then potentially have a shorter life. And finally, of course, knowing when the bearings are expected to fail is giving you input on when do you need to book the big ship for getting the jackup vessel to replace these main bearings. And that will actually be the input for the cost model that Clemens will now explain you. So thanks for now, and over to you, Clemens.
Thanks, Asger. Actually, before handing over the discussion to Clement, there are a couple of good questions posted by the attendees. So Asger, let's address those questions. Is that okay?
Okay, yeah. Should I try to get the chat to? Okay.
I can read it for you.
Okay, maybe if you can pick what you think is the best, then.
Okay. Okay. Yep. Thanks. So Ken Bettis from Alliant Energy. So he would like to know more about the impact of turbulence intensity in increasing bearing life, because typically in the industry perspective, as per theory, it should impact the bearing life negatively, but I think some of your results are showing it increases bearing life. So can you please comment on that?
Yeah, the way we're thinking of this is this is the bearing loads obtained from the air elastic simulations. So in order to evaluate the life of the bearing, you basically need to ask yourself, what is the load? Yeah, do I have a cursor here? Maybe I do. Boom, boom, boom. Okay, but if you look at the right-hand graph, you can see that's the bearing load as function of mean wind speed. So basically, we're asking ourselves, how many revolutions are the main bearing running at the different loads? And what we get from the life evaluation is definitely that we're consuming the most of the life by sitting just at the peak of this thrust curve. But if we now increase the fluctuations, or if we increase the turbulence, you might say that we will be spending less time at the top of the peak, and we will be spending more time sort of down the ridges of this peak. And hence, when we start evaluating for how long time or how many revolutions are we doing at the different loads, it seems to us that the turbulence is moving you away from that painful point. And that is why we see that the life of the main bearing is actually increasing. Of course, you can sort of always question this in terms of, well, this is a replicate of the thrust curve. So in order to have the thrust curve coming down, you need to get your pitch control system to start pitching the blade. And I agree that it gets a little bit complicated because now it might be something about the implementation of the specific pitch control, which is only the, let's say, academic DTU 10 or the DTU, let's say, academic controller of how to do the pitching. It is not, we have not tried to replicate what the turbine is doing. I should say that. Was that a try, or I hope that was enough to try to answer the question.
So Asger, is it okay to say, based on the inputs that you took into the model, based on the assumptions that you took into the model, based on the shift in wind speed, moving away from the peak, which is around 10 to 11 meter per second. So turbulence intensity is pushing the wind speed, average wind speed, lower or higher than that, and that's why you're seeing a slight increase in expected life on the main bearing based on your inputs.
We might say we are fluctuating away from the peak of this mountain here.
Yeah.
That's kind of how we see it. But of course, the pitch control is doing that. Yes.
Okay. Sounds good. Yep. So Ken, yeah, does that answer your question? If not, yeah, please have the follow-up questions on it. And Greg Petrick, he has a question on grease cleanliness. So his question is it a function of air quality, or is it something that got induced into the grease before installation, maybe while waiting in the inventory? Yeah. What is this grease?
Basically, you can kind of say that in principle, super clean grease has this EC factor, or the EC number as 1. Normal cleanliness is usually said to be 0.7, but when you inject the grease into the main bearing, it will actually, be polluted by metal debris as you operate your main bearing. And then the EC number is actually expected to go down. Of course, on these turbines, you have an automatic degreasing system, which is kind of pushing in. Let me just show this thing here. It is basically taking these cartridges that you transfer into a big container, and then there's an automatic system pushing in grease into the main bearing, and of course should sort of push out the dirty grease. But you kind of rely on that is all working, and one way to really get the life to decrease on these bearings is if the grease gets dirty. And I mean, it has been very interesting also now to discuss this with EDF in terms of what is their maintenance strategy on these main bearings. And according to EDF, they would actually flush these main bearings if they see any signs of having problems with the grease. So you can kind of say that they are doing a better maintenance than what you would expect from just running the ISO 281 standard. But grease is definitely something you should keep an eye on, and we are trying now to let's say, see if we can exchange some information with EDF on the grease cleanliness from these turbines.
Yep. Thanks, Asger. I think there is a follow-up question from Ken Betis. Commissioning of wind farm is around 2011. How was the actual failures compared to this calculation? So they're already running for almost maybe 13 years, the wind farm. So how does your predictions correlated with the actual field failures? I think that's a good question. Yeah, go ahead.
Yeah, maybe I should be careful to not reveal something I shouldn't do. But I think I don't think I'm revealing too much if I'm saying the observed failure rates are lower, slightly lower than what we have, or is lower than what we have predicted here. One way of interpreting that is exactly this flushing procedure, where you can kind of say that if you flush out all the grease, is that actually, you know, better than what the ISO 281 is actually prescribing? So they are actually doing better than what we are predicting here.
Yeah, and also Asgard predictions are full replacement of the main bearing.
Yes.
So in general, as you guys know, there could be main bearings running with damage, but you can extend the life by regreasing, by flushing, like as Asgard mentioned. So Asgard predictions are full replacement, but not covering the ones that are running with damage.
Yes, true.
Any other questions? If not, we'll keep watching the chat window. Great discussion, great questions. Thank you for that. And I'm going to hand over the discussion to Clement. Thanks, Asgard.
Yeah, thanks.
Okay, thanks, Raja. Thanks, Asgar. Thanks for the good discussion and the question in the chat. We are going to move to the next part of the presentation. Yeah, as I'm switching through the slides, I think one important point there is what Asgar just mentioned, is this kind of up to 3 or 4 main bearing failures over the 35 years of operation for that wind farm. So maybe like a little bit optimistic compared to what's actually happening on that farm. It can be due to the different OEM strategies, but yeah, just remember that site-specific information of like 3 or 4 main bearings, and then we can compare that to what I'm gonna show in the next slide, which is considering like industry data and stressing the need for having more site-specific data you can access. Okay, so I'd like now to switch gear a little bit and trying to understand like how those kind of models. So as I get this very detailed presentation focusing on the main bearing, which is one component of the wind turbine. And of course, if you are talking about competitiveness of wind energy, you want to focus on the turbine system as a whole, on the wind farm system as a whole, even I would say. So the question is, once we're getting those inputs from those different models, like how do we actually implement that in a bigger picture, and how do we actually look at the impact it has on the cost? So I just want to present the concept, or how we are trying to address that question in Hyperwind. So looking at the turbine assembly, so it's kind of if we are talking about the main components, so the gearbox, the main bearing, those components that are allowed to fail throughout the lifetime. We're not talking there about the tower or the foundation. Those they need to stand yes throughout the entire lifetime. But you accept that you may need to replace a few main bearings over the lifetime of your wind farm. So this is really like the focus of what we want to discuss today. So yeah, you can derive by this nice model the failure probability, which answer that very simple question, saying like after a given number of years in operation, how many failures do I need to expect on my wind farm? So you want to know like your wind farm is installed right after COD, you expect little failure, except if you have infant mortality. But then as the wind farm operates, as I mentioned, you can have like those metal debris going into the main bearing, and then the life is going to be reduced, and you will start to see the first failure. So if you want to know, if you want to plan your OEM strategy based on that, that's what you need, this probability of failure. And also you want to know what is the impact of that failure. So what are the consequences of a component failing? So first of all, there is the cost, because then you need to replace that component. So you need to buy a new one, you need to ship it. You also need to pay for the technicians going there. So that comes at a cost. And also there is a downtime. So if you're not ready to replace that component straight away, if you need to wait for the supplier to deliver a new component for you, then the turbine is off during that entire period, and you're losing some annual energy production. So the first part of like how much of a component costs gives you an estimation of your operation expenditures. So like if at a given year Y, you're able to know which is how many components you need to replace. So all those components, the blade, the main bearing, the generator, the gearbox, all of them, you know, like how many of them you need to replace. You know the cost of one replacement. Then the OPEX for that given year is simply the sum of all those individual operations. So we're kind of doing there like an assumptions that you cannot optimize on the ship and sense multiple components at once. So it's probably a conservative way of looking at things, but at least it gives you an idea of how much you will spend. And so on the top of that, there are obviously some other expenditures that we consider as fixed. So just like how much does it cost to operate the wind farm? So I've also represented those on the plot that you see here. And we are not covering like maybe all the components. So there is also kind of a fixed maintenance cost that we are applying. So this is derived from EPRI's 2022 wind status technology cost and performance. But yeah, looking at the picture here, I'm just showing, so it's the translation of that equation for each of the components of the turbine. And this is what you can see here as for that Teesside wind farm. So using the Siemens data that we have in the winner reliability database, estimating the cost of the replacement of those various components throughout the years. And so you see the cost kind of increasing as you go with time and your component ages and you have more and more replacements. And you can compare that, for instance, to the operating cost of the wind farm, that purple line here, and what we classify as the fixed maintenance. So which represent like a fair 50% of the total operational expenses. So that was for the OPEX. Now the other part is how do we model like the availability losses? So as I say, like when the component is done, there is a downtime. So part of it is like just the mean time, what we call the mean time to repair. So the time after the failure, when you're actually starting to replace that component, and then there is the repair time, which is the time it takes to replace that component. So that gives you like the downtime for one failure. So then the total downtime over the course of a year is just the sum of the downtime on each component. And so once you have that, you can compute the wind farm availability, which is over the 8,760 hours of the year, like how many are spent for each turbine down because of waiting for components replacement. So that gives a fraction that then can be applied to the annual energy production, the theoretical annual energy production, including all the losses, to get like an effective annual energy production, which is what you would expect given that you're having the failure at a given year. And so the graph here shows the example for that Teesside wind farm, where we see like the downtime due to the availability losses, so just the downtime normalized for each of those components. It's interesting to see that, for instance, the generator is not the one that were causing like most of the costs, just because the price of the components is not necessarily high, but because you have a larger lead time. Every time one component fails, you need to wait for a longer time. So they're responsible for more of the downtime. So those parameters are also interesting to look at, and that stress the need to consider the thing in a holistic manner if you really want to know in the end what's the impact on the cost of the technology. And yeah, one thing as well that is I'd like to point out is that for the main bearing here, like if we this orange line represent every time you have a failure, then you have like a given downtime, and that translates to the availability losses. So behind that there is the number of failures you have each year. And so if we add those failures, we get to something which is around 15 or 16 failures through the entire 25 years, which is to compare to what Asger was mentioning of those 4 failures a year for that specific wind farm and on those specific conditions, 4 failures for the entire lifetime, sorry. So that's stressing the need to get like as accurate, as site-specific accurate information, because there we're using the entire industry-wide data that we have in the database. So that gives you an idea, a ballpark idea. But maybe for that wind farm, the wind conditions are not that aggressive, and we're comparing for wind farms that are having much higher aggressive wind conditions. Also, maybe it's coming from the fact that those are onshore turbines, allegedly much easier to access and replace the main bearing that offshore, where you need like a ship to ship things through a vessel. So that's really where like getting those models that Asger just mentioned really comes into play and allows you to make like a better estimation on the cost. Yeah, just like on a few words on the Teesside wind farm, so that you've heard about it a lot from the beginning of the presentation, but just what are the important points? So it's this wind farm on the very close to the shore of the UK, somewhere over here. I'm not gonna dare and trying to guess which big city is close. I'm not an expert in the UK geography, but it's relatively close to shore. It's the 25 turbines, Siemens 2.393, relatively old model, commissioned about 10 years ago. So we have like a good amount of data. The AEP, the raw AEP is about 235 gigawatts. So that's a result of a simulation with a net AEP of around 2.15 gigawatt hours. Those are wake losses and electrical losses that we have included in that simulation. And that gives like a capacity factor of roughly 40%. So it's a relatively high availability wind farm. And so now the exercise would be to try to calculate the impact of the component failure on the cost for that technology. But before doing that, we need to fix like a few things on the problem, because the LCOE, as I've mentioned at the beginning of the presentation, incorporates everything from the capex to the opex, and also like some financial assumptions, what is the interest rate and so on. So I don't want to dive too much into those data for today, but they're just there like for reference. I used for this exercise the recommendations for the year 2023 by the Department of Revenue. So that fixed basically what interest rate to consider when you want to compute your levelized cost. Also, what's the cost of equity? What's the typical debt to equity ratio? Really, those are kind of frozen in this exercise, but just that if we were to change that to make it like site specific, that's also something we can very easily do in the tool the way it is. Same for the capex. There I used a very standard breakdown of the turbine component and BOP components. So kind of a blend between the NREL cost of wind energy 2020 publication. It could be updated by the more recent data, but overall it does not change that much. And it also incorporates some slight change that are from April's report of 2022 wind status cost. But overall, it's like around $1,300 per kilowatt of installed power. And it's roughly the BOP is about like a good 60% of that cost. This is because we're talking about offshore, so it comes from assembly, like shipping things to the site, and also like the foundation is pretty expensive, and so on. So that's why typically when you look at an onshore site, you will find the turbine proportion to be quite high, but it's not because the turbine is cheaper here, it's because the BOP is actually much more expensive when you go offshore. So with that shown, we now have like everything we need to compute the LCOE. So I have summarized those results there. We get to an LCOE of roughly $116 per megawatt hour produced. It's close to an half between like the capital expenditure and the operational expenditure. Capital are about 67% and $67 and $50 for the OPEX. But you can see that, yeah, that's kind of also because most of the OPEX, the bigger OPEX arrive relatively late in the lifetime of the wind farm, and because we are kind of levelizing everything to the first year, so it's really kind of an exercise you do once when you look at the potential of one solution. We are converting everything in today's dollar, and $1 in 20 years or in 50 years is worth much less than $1 today. So that's kind of this effect that kind of shrinks a bit the OPEX. And so those are things you also want to consider when you're looking for different financing options that can actually change the results quite a bit. And we see there as well the availability dropping, peaking to a minimum at some point, which is when you see like your operational expenses being the highest, because that's the year you're replacing most components. In that case, it's because of the blades. And yeah, it increases a bit after because the peak of the blade replacement has passed. So that's kind of a baseline scenario. And now we can use that to compare like new scenarios where, for instance, we will replace the component, the failure probability of the main bearing using the site-specific data that Asger just mentioned. So switching from that 16, 17 replacement to this 3-4 replacement a year. And so what is the impact that this will have on the technology? But also in terms of next step, Hyperwind is just not about this OEM planning and optimization. So just want to highlight what the rest of the team has also worked on and what we are also going to factor in that LCOE. So we mentioned about reduction on the OPEX, but there is also reduction on the CAPEX, because like a significant part of the project is about getting smarter at designing the turbines by introducing probabilistic design. So the concept there is really you design the structural components, the tower, the foundation for a given lifetime, or for a probability of failure after a given time, which is the same thing. And so how this is done is you will get a distribution of loads and a distribution of strength of your material, and the intersection between the two is the failure probability. And if you reduce uncertainty, the load probability of distribution is going to become like narrower, and so it's peaking because the integral here is summing to 1. It's not, the load are not increasing, it's just we have higher probability that the actual load is something over here, and so that's reduce the intersection. So if you want to keep the same lifetime or the same probability of failure, what you can do is simply reducing the material mass, shifting the distributions towards the left here, and saving cost on the CAPEX. So we received recently with the from the other work package significant reduction on those components, and we are going to assess also what would be the impact on the LCOE. And yeah, another deliverable, immediate deliverable of what Asger present is, if you know when your components are more likely to fail, then you can better plan the OEM. And so that comes by also getting smarter at predicting the weather conditions, so to know when you will actually be able to go on site. So reducing the delay to go on site and anticipating the failure, so you can plan for those things in advance and reduce the cost, and come with a better scheduling, and you reduce the cost and you increase the downtime, and then you increase the productivity of the wind farm in the same interval, and all that reduce the LCOE. So we are kind of wrapping up on those work package as well, and we'll soon implement those changes in the LCOE tool that we've just presented, and hopefully we will share results on the final event in June that Raja just mentioned. Okay, so that was all for that part and for the presentation. So if I go quickly through a summary, Asger did this very interesting presentation on the advanced reliability model for the turbine components. So this physics-based model trying to assess what is the lifetime, the remaining useful life of the main bearing based on the loads, on the axial and radial loads on the turbine. Also quantifying, coupling this with site-specific information to get this reliability map and know how much of the life you actually consume for the site, and getting like to a much more accurate prediction of the component failures for that site. And then we have demonstrated the framework where you could take those inputs, those outputs from Asger simulation and implement that into a bigger picture and try to assess the cost on your OEM. And if you were to compare that to see the competitiveness of the wind energy, then you could compute the associated LCOE and compare to the baseline scenario we've just presented. So that's not the end of the story. As the next step, so we are planning to assess the LCOE reduction for all those benefits that Hyperwind is delivering. So the mass reduction, the better scheduling. We will have a dissemination session on the Hyperwind at the Wind Europe Technology Workshop in June in Dublin. So it will be actually right after the conference on the afternoon of the 11th of June. Yeah, so if you're interested, then I think it will be open to the public. And yeah, those tools that we have presented, at least the LCOE part, we plan to make that an online wind economic tools that will be hosted. It remains to be defined exactly what will be the detail and which level of detail we could make available, but at least the main framework should be made available to anyone as a deliverable of the Hyperwind project for you to assess the the economical competitiveness of different solutions. So stay tuned for more updates on Hyperwind. And with that, I'll hand that over to you, Raja.
Thanks, Clement. We have a question for you from the chat.
Sure.
It's from Irene. At the beginning, you mentioned as a project objective the reduction of WACC through increased bank confidence.
Mm-hmm.
Are you able to address this aspect in the project somehow with the relevant stakeholders? I think that's a good question.
Very good question. I think so. No, I don't think we have initiated discussion with with bankers to see whether they will be willing to reduce the interest rate. But that being said, one thing is that, as I understand, one big driver for the interest rate that is given to a project is the difference between the P50 of the AEP and the P90, because then that kind of gives the variability between the variability in revenue you can expect, and banks, they don't like risk, and so if you have like a project with high risk, they will charge you with a higher interest rate. And so with Hyperwind, what we can do is to narrow the distribution, because we're getting better at predicting the components, we're getting better at anticipating the maintenance. So we're reducing all those availability losses, and we are also getting more accurate wind conditions and less uncertainty throughout like the AEP assessment. So all in all, it's gonna bring to a narrower distribution on the AEP, and we can hope it will help reducing the weighted average cost of capital.
Thanks, Clement. Yeah, as Asger and Clement has mentioned, the outcome of this Hyperwind project will be shared with the public. Those details will be posted on Hyperwind website that we have included in the slides. And also, the Hyperwind project is a cohesive model. What we mean by that is it links the oceanography, the loads on the main shaft, moments and forces, how it get transmitted into the individual components and impact its reliability, and how these reliability models can be used for optimum momentum modeling and also reduce your costs. So it's a very comprehensive approach. The individual modules are being developed by multiple organizations, research institutes, as we mentioned upfront during the discussion. In case if you have any model that you are working on, you can always plug that in and replace with the one that we have developed under this Hyperwind. So this modeling up, the main goal is to develop this framework modeling approach, and that can be easily updated or modified with any new models that you are building. So that's one of the goals of this effort. And also, yeah, if anyone is planning to attend Wind Europe Technology Workshop, that's in Dublin. I think we are planning to have the dissemination, maybe 2.5 hour session on June 10th. Is that right, Asger? Is it June 10th? Is it confirmed or?
No, it's 11th.
It's 11th. Okay.
It's
It's
11th.
11,
So
yeah.
So the
Okay.
conference ends at 3 p.m. I think the last session, and then we are straight away we are starting with the Hyperwind final event.
Yep. Good. So yeah, you don't need to make a separate trip for this. So if you're planning to attend Wind Europe, or if you're planning to attend Hyperwind, you can also attend Wind Europe Technical Workshop. So 2 events in one trip. So please plan to attend the dissemination session. And if you're interested to know more details about it, please contact us and we'll share the information and agenda with you. With that said, any further questions for Clement and Asger? We'll just stay here for maybe a few more minutes to see if there are any further questions. Thanks again for joining.